Welcome to Chapter 7 lecture video. Today we're going to talk about chemical reactions. So in Chapter 5 we talked about chemical formulas and balancing charge. Then Chapter 6 we talked about mole ratios within a chemical formula. Now in Chapter 7 we're going to use those chemical formulas to make chemical reactions. And so grams to moles, moles to grams, this is going to be our most important calculation moving here on forward. We're going to do this for everything. We're going to use this in our reaction equations or our chemical reactions. So chemical reactions or chemical reaction formulas, chemical equations, these are all synonymous terms. This is how we're going to communicate how chemicals change from one species to another species. We're going to touch on solubility and polarity. Polarity is kind of what describes what things will be soluble in what solvents. And then we're going to have a few types of reaction types. We've talked about a few of these in the labs. So we had precipitation reactions that we discussed where we had, sodium nitrate and calcium carbonate. Calcium carbonate was the one that precipitated out of the reaction. We mixed the two precursors and they switched places to do a double displacement reaction. So we like to represent the high school or middle school chemistry reaction using, acetic acid, baking soda, and some food dye to, represent a volcano. And so this is our classical gas reaction or gas evolution reaction. And so this is a very fun one that the book likes to point out. The combustion reaction or the redox reaction is probably the most common reaction. Your cell phones and the combustion engine all do redox reactions. So this is where we have a transfer of electrons from one thing to another thing. Electrons is what powers our electronic devices. Ultimately, it's also what powers most engines and motors, whether it's an electrical motor or a gas engine. So, laundry detergent. So, what we use laundry detergent and these water softeners for is to prevent soap scum or to prevent precipitation reactions. So, precipitation reactions are the class of reaction that we've seen in the lab. And so, here's an example of some calcium and magnesium deposits. Calcium is the salt that we saw deposit in the double displacement reaction last week. So, should be getting familiar with these. There are plenty of things that signal a chemical reaction, but what is a chemical reaction? A chemical reaction can be defined when an element or molecule changes place or combines with another element or molecule. And so when we're lucky, there's a very indicative change that occurs. A color change, a precipitation, like we saw in last week's lab, a evolution of gas, like in the, acetic acid and baking soda volcano, an emission of light, or an absorption or emission of heat. A combustion reaction, if you light something on fire, it gives off a whole bunch of heat. That's your indication of a chemical reaction. There's also light and other things, but there's several things that can indicate a chemical reaction. So here's a few visual indications. You can kind of pause and zoom in, but we have a color change. Very obvious something's going on here. There's also a whole bunch of heat or maybe gas being released. It's hard to say which one. Precipitate, we've seen this. Gas evolution, we will see this in the future. A glow stick or, a combustion reaction gives off light or light and heat. So what's not a chemical reaction? Physical changes. Remember, we talked about chemical changes, physical changes. Chemical changes are chemical reaction, where elements change or chemicals change places or combine. They form new forms of matter. They become something different. The atoms rearrange themselves. Boiling or a change of state may look like a chemical reaction, but it's not a chemical reaction. So, how do we define chemical reactions? We have some reactants, or I typically refer to them as starting materials, and they convert into products. Now, we can provide more and more detail for these chemical reactions, but this is kind of the base skeleton of what a chemical reaction is. We have abbreviations for the physical state of matter, so gas, liquid, solid, and aqueous. Sometimes you'll see P for precipitate, but I would just always use solid because solid is applicable to a precipitate or just a standard solid. So aqueous is what we apply to something that's dissolved in water. When we form water out of an aqueous reaction, we refer to it as a liquid because we're forming a small amount of water, and water is what it is, so we just define it as a liquid. Little caveat. Now that we have these physical state designations, we can include this with our reaction scheme. Now, you'll notice that if we count the amount of atoms we have on both sides, we don't have an equal amount of atoms on both sides. This is true for oxygen, but it's also true for hydrogen. The only thing that we have an equal number of on each side is carbon. And so we can't just create or destroy matter. We have the conservation of mass, matter, energy. All these things are kind of synonymous with each other. So we can't just create oxygens out of nowhere and eliminate hydrogens into nothingness. So this is what we would call a skeletal equation. We need to balance this chemical equation. And so the way we do that is we increase the total number of molecules. So we can't just have one molecule of methane reacting with one molecule of oxygen to give us one molecule of CO2 and one molecule of water. The ratios or the stoichiometry of these is going to be slightly different, and we need to figure out what that is. The way we do that is by putting these leading coefficients for given elements. So we put a 2 in front of water and a 2 in front of oxygen, and this indicates that we have 2 molecules of oxygen for every 1 molecule of methane. These react or combust to do a redox reaction to form 1 molecule of CO2 for every 2 molecules of water. So this would be called a balanced chemical equation. We have rules for how we balance these, and we'll get into that. So if we count everything, we have the same number of carbons, same number of hydrogens, same number of oxygens. I recommend that you do some type of mass balance table. When I say mass balance, I'm just talking about, we have 1 carbon to 1 carbon. Those would have the same masses. 4 hydrogen to 4 hydrogen, they would have the same masses. 4 oxygens to 4 oxygens. Everything is balanced in terms of the amount and the type of atoms that we have. So now we can see that this is how we want to represent a chemical reaction, and we can move forward and do more calculations. We will actually apply, mole to gram and gram to mole calculations in chapter 8, but for now we're just going to focus on balancing these chemical reactions. So the book has 5-ish, there's really just 3 real steps, 5-ish steps. I have 2 steps. You can read these, and I'll keep these slides up here, and you can pause them and write them down. But my 2 rules are, if you have a pure element, balance that last. Everything else, you balance based on electronegativity. Balance your least electronegative element first, remembering to balance your pure elements last, and balance your most electronegative element at the very end. Then, once you've done all of that, balance your pure elements. So you can pause and, write these down. Essentially, those 2 rules that I've given you apply to all these. The first rule the book gives you is have, balanced chemical formulas. You have to have charge balanced formulas before you can do a chemical equation. So you have to have your chemical formulas before you can do your chemical reactions. But, you gotta walk before you run, so to speak. And then, obviously, at the end, you got to check, make sure everything's balanced. But if you start with your least electronegative elements first, and then move your way and up in terms of electronegativity, and balance your pure elements last, you'll always cover all your bases. Now, if you forget these rules, you can just always make sure that you have the same number of atoms on each side of the chemical reaction. The starting material has the same number of atoms and the same type of atoms as the products. That's good. If you do it against these rules, you might end up kind of cycling back and forth and having a little bit of frustration or redundancies. So here's an example. We have a skeletal equation for aluminum reacting with sulfuric acid to make aluminum sulfate and hydrogen gas. However, you'll notice that the number of sulfates is not the same. The number of aluminums is not the same. Hydrogen is fine, but we're going to have to, rearrange this, so to speak. So the first thing we want to do is start with our least electronegative element that's not a pure element. So the only thing that's not a pure element is our sulfates. So our sulfate has 3 on the product side and 1 on the starting material side. So we'll put a 3 in front of there, and that will balance out our sulfates. However, it's going to unbalance our hydrogens. In order to get our hydrogens balanced, we'll have to adjust that, and then we'll want to adjust our aluminums at the end. So we put 3 hydrogens in here because we have 6 hydrogens here. We need 6 hydrogens here. We'll put 2 aluminums here because we have 2 aluminums over here. You could balance aluminum first, you could balance hydrogen first. It doesn't really matter. Technically, aluminum is less electronegative than hydrogen, but you might not think of that just based off of the rules of increasing from bottom left to top right. Hydrogen is a lot higher than aluminum, but it's a lot further to the left. They end up having a very similar electronegativity, and ultimately, as you can see, it wouldn't have mattered which one we balanced first. But technically, you should balance aluminum before you balance hydrogen. So we could do our mass balance and make sure that everything equals out. So we have 6 hydrogens to 6 hydrogens, 2 aluminums, 2 aluminums, 3 sulfurs, 3 sulfurs, 12 oxygens, 12 oxygens. Now, if you have a polyatomic that stays intact like this, our sulfate is in the starting material, it's in the products. It maintained its integrity throughout the reaction. And so we don't have to worry about balancing each sulfur and each oxygen individually. We were able to balance the entire sulfate across the reaction. We're going to talk a little bit about solubility. So we've discussed this in class a little bit, but formally, solubility means the ability to dissolve in something. This is a physical property, not a chemical property. So does something dissolve? It's related to the chemistry, but it's not a change in the chemical composition. If something's insoluble, it doesn't dissolve. Again, a physical property would be insolubility. Aqueous solutions are fully dissolved or homogeneous mixtures in water. Ionic compounds are very soluble in water, and so we call these electrolyte solutions or, dissolved salts. An ionic solution is any solution that has positive and negative charges that dissociate in a solvent. So sodium chloride is very soluble in water. We would call it a strong electrolyte. Electrolytes are any type of salt solution or any type of ionic solution. The more you can dissolve the salt, the stronger of an electrolyte it is. Sodium chloride is one of the stronger electrolytes out there. And that's a good thing because it's very important to biochemistry. If you had 100% pure water, deionized water, like we have in the lab, it would not conduct electricity. However, if you take regular tap water or ocean water, something that has dissolved ions, dissolved salts, you can conduct electricity because the electrons can actually flow through this solution, from positive to negative, and connect the circuit, so to speak. We're not going to focus on electrolytes and, conductivity, things like that. It's just something that you should be aware of. So silver nitrate is a strong electrolyte because it fully dissolves. The polyatomics stay as the polyatomic. This is why we always treat them as a, individual unit, is because they don't ionize like silver and chloride would. Silver and nitrate stays intact. It's an entire polyatomic unit that is a -1 ion. So silver chloride, the non-polyatomic version of silver nitrate, is totally insoluble. And so water, the partial positives and the partial negatives on oxygen and hydrogen are not strong enough to fully dissipate the positive and negative interaction from silver chloride. And so sometimes the electrostatic interaction of the cation and the anion is stronger than any solvent or your given solvent can overcome. And if it's not a strong enough solvent, it just won't dissolve the salt. That's the case with silver chloride or calcium carbonate, as we saw in last week's lab. So we have solubility rules. I'll give you these tables. You're not responsible for memorizing them. What I recommend is that if you are going to do more chemistry classes, you will need to be aware of these things. So memorize one of the rule sets. Either memorize what's soluble or what's insoluble. If you know one side of the equation, you're going to be able to back out the other side. If you know what's soluble, everything else is insoluble. If you know what's insoluble, you can bet everything else is soluble. So here's the solubility rules. You can, pause and copy these down. They're obviously in the book on table 7.3. Here's a flowchart for solubility. Here's a flowchart for insolubility. So again, memorize one. You don't need to memorize both. You'll kind of confuse yourself or, mix things up if you're memorizing both right from the get-go. So we're going to talk about a few different classes of reactions. We have the reaction that we saw last week, and pretty much the only chemical reaction we've done at this point, the precipitation reaction. So a precipitation reaction is formally where you have two dissolved solids, you mix them together, they do some type of displacement reaction, either a single or a double displacement. This is an example of a double displacement where potassium and lead switch partners. When they switch partners, one of the elements is incredibly insoluble or entirely insoluble and becomes a solid again. So you can see this very visually with lead iodide. Transition metals are very colorful depending on what they're bonded to. So lead nitrate is clear and colorless. It might be slightly dingy yellow color, but not quite as profound as the lead iodide. Upon contact, you can see there's clearly a reaction. So precipitations are our favorite type of indication of reactions because it's very obvious. Now, if you're boiling things, yeah, you might have a little bit of sedimentation or precipitation from, evaporation of your solvent, but usually you control for things like that in a reaction. The nice thing about precipitation reactions is that you can always predict what the insoluble product is by just looking at your solubility rules or looking at a solubility chart. We'll have a lab, I think it's lab 6 or lab 4, where we'll have a solubility chart to reference to see which product is precipitating out. So if you have these dissolved salts or these solutions of potassium iodide and lead nitrate, they fully dissociate or fully ionize into their respective anion and cations, and those float around into solution. They might bump into each other, but they're going to bounce right off. However, when we mix these, when lead and iodine interact, the interaction between them is going to be so strong that they form an insoluble compound. We designate this with the phase. It goes from AQ. We have a double displacement. We get lead iodide. Now we're going to represent that lead iodide as a solid. There's such a strong interaction between these two things that lead iodide interacts. It doesn't stop interacting. The water can't come in between the lead iodide crystal lattice, and it'll just sink to the bottom because solids tend to be more dense than liquids, and metals are definitely more dense than non-metals in terms of higher on the periodic table versus lower on the periodic table. So we have double displacement reactions and single displacement reactions. Our precipitation reactions are always going to be one of the two. If we have two binary compounds, we'll have a double displacement like this reaction here. If we have one binary compound, something made of two separate ions, cation and an anion, cation, anion, we'll have a double displacement. If we have a cation and anion reacting with a pure element, then we'll have a single displacement. And those happen, but they're a little bit more rare. Obviously, elements are not the most common thing, so reactions with pure elements are also not the most common thing. In this case, we would look at a solubility table to predict which one precipitates out. We know that sodium chloride is not insoluble, just from everyday experience. That's table salt. Salt dissolves very readily in water. If you've ever cooked, you should be familiar with this. Copper carbonate, you've probably never interacted with. Carbonate salts tend to be insoluble, and copper carbonate is especially insoluble. We would know this only by practical experience or by referencing a chart or memorizing these rules. So in here we have sodium carbonate. It displaces copper, or you could think of it as the anions displacing each other. I'll usually refer to it as the cations displacing each other because that's just the first one. It's the first one I look at. It's the first one I think about displacing each other. Copper carbonate will be insoluble, sodium chloride will be soluble. If you have something like this where you have a predicted insoluble salt and you don't see a precipitate, it's likely that the reaction didn't occur. So at the end, we want to make sure that everything's balanced. Even though, we went through all the, process of making sure that this is a solid and everything else is defined as aqueous, we need to remember to put our stoichiometric coefficient so that we have the same number of atoms that we started with as we finish with. So we have multiple ways to represent chemical equations. We've been just talking about standard molecular equations or chemical reactions. We also have what we are going to refer to as complete and net ionic equations. Complete ionic equations are where you ionize every ionic species into its representative ion. So we'll take silver and turn it into the silver cation, nitrate into the nitrate anion, sodium, and so forth and so on. So it'll look something like this, where we separate everything into its cation and anion. Again, we're never going to break up our polyatomics, so we keep that as an individual unit. It's a good idea to put parentheses around it so that we don't mistake our minus for a 3 minus on accident. We can get sloppy sometimes and it looks like that we have a 3 minus for an NO species. Put your parentheses around the polyatomic, charge in the top right corner. So that's the complete ionic species. You'll notice that silver chloride, the insoluble species, we write that as a single compound. Since it doesn't ionize in solution, it doesn't get the same treatment in the net ionic equation. We only show ionized compounds. So the ones that just kind of sit around in solution, that don't become a solid, they don't go from aqueous to solid, they don't go from ionized to non-ionized, we call these spectator ions. So the difference between the complete and the net ionic equation is that we remove the spectator ions from the net equation. The net equation is just there to show you what reacted to form the precipitate or form the new phase. We can do these net ionic equations with gas evolution reactions as well as precipitation reactions. However, we're showing it with a precipitation reaction right here. So we have our molecular equations. This is typically how we're going to talk about chemical reactions. Complete ionic equations and net ionic equations are used for certain niche applications. We'll revisit these in chapter 16 for redox chemistry, but essentially we'll have a couple problems where we just fully ionize our chemical species, showing that we know the difference between complete and net ionic equations. Again, our complete has all of the spectator ions, the ones that just kind of float around in solution and don't precipitate or evolve as a gas. And then the net ionic is we remove those spectators. So the next form of reaction that we're going to talk about is acid-base, sometimes referred to as neutralization reactions, but a neutralization reaction is slightly different. So an acid-base reaction is simply where you have an acid, a base, they react. Just as simple. The difference between an acid-base and a neutralization reaction is a neutralization reaction, by definition, takes an acid, a base, to react to give you water and a salt. You can have acid-base reactions that do not form water and a salt. Those would not be defined as neutralization reactions. Slight difference. So for us, we are going to think of acid and base chemistry as H plus and OH minus, or hydroxide. So hydrogen ions or protons can combine with hydroxide anions to form water, or what's really happening is that water forms these other species. We can kind of split water into these, or two molecules of water can combine to form a hydronium ion, which is H plus added onto water, and a hydroxide anion. We'll talk about this a lot in chapter, I believe, 15, maybe it's 13, but in unit 4. There's some physical characteristics of acids and bases. We don't care about how they taste, feel, and smell. Here's some examples of acids. We've talked about how to name them. We have the binary acids. Well, we have our bases as well. So hydroxide is our quintessential base. Any hydrogen atom is our quintessential acids. In this class, we can think of acids as proton donors or hydrogen cation donors, and bases as hydrogen ion acceptors or proton acceptors. So you could add a proton to sodium hydroxide, it would become water and sodium chloride. So we have our acid base or our neutralization reactions here. So just like everything, we need to make sure our equations are balanced. So the number of hydrogens is not the same on each side. We have 1 and 2, and then we have 2. So 3 versus 2 is not the same. We need to balance them. Remember, our pure elements get balanced very last. We don't have any pure elements here. We want to start with our least electronegative element first, and then move on. The book doesn't do this. They get similar results. They start with hydrogen. I would start with calcium here. However, calcium's already balanced, so we don't need to work with that. We can just go straight to hydrogen. Next in our number of reactions that we're going to cover is the gas evolution reaction. So here we have 2 examples, making some dihydrogen sulfide gas from sulfuric acid and lithium sulfide, and then making some CO2 gas from some sodium carbonate and hydrochloric acid. Now this is a 2-step reaction, whereas the top one is just a 1-step reaction. Carbonic acid is what gives soda and carbonated beverages the acidic bite or the carbonation. And so this chemical is unstable, with generation of water and CO2 being its more stable product. So here are a number of different polyatomics that tend to turn into different gases. You don't need to memorize these, but you should be familiar with this one of any of them. But in general, the more chemistry you do, the more you should memorize these type of polyatomics, naming, things of that nature. So here are reactions for these given gas evolution precursors and molecules. These would be the gaseous molecules. These would be the precursors on this side, or the starting materials would be the precursors. The products would be the evolved gases. So we can, take a whole variety of these, and it's a great way to indicate a reaction. So if you see little bubbles forming from the reaction, it's a great indication. As long as you're not boiling something on top of that, then it can be kind of hard to determine it. But, just another reaction with the sulfate ion. So sulfite, not sulfate. I apologize for that. The sulfate ion is much more stable than the sulfite ion. This sulfite ion is prone to decomposing into sulfur dioxide, so it loses one of the oxygen. That oxygen gets picked up by the proton on the acid and becomes water. So we want to balance these as always, and so we start with our least electronegative element first. In this case, that would be potassium. We don't have any pure elements, so we can just go on the electronegativity scale. Start with potassium, then move to hydrogen. If we have to, we can move to the sulfite ion, and then the nitrate ion. Oxygens and waters. Again, sulfite breaks apart. So in this case, we wouldn't be able to just go from sulfite to SO2. We could go sulfite to hydrogen sulfite, but from hydrogen sulfite to SO2, you would have to balance each individual element because the polyatomic is breaking apart. For nitrate is just a spectator ion the whole time. It's just there to stick around. You can balance nitrate as nitrate as nitrate. So we would do this. We'd get a 2 in front of the nitric acid. We'd get a 2 in front of the potassium nitrate. And then we would get a 2 in front of the potassium nitrate at the very end. And that would be really the only stoichiometric coefficients here. The most common acid-base chemistry that most people do who don't work in an industrial setting, if you do acid washing or things like that, you'll absolutely deal with those things more than you'll deal with antacids. But antacids are either hydroxide or carbonate bases that react with the stomach acid to do a neutralization reaction. If you tend to burp a lot from your antacid, it's a carbonate acid. If you tend to have to urinate a little bit more, then it's a hydroxide base. It's producing water from the acid in your body. So our next class of reaction is redox. We'll cover this as well as acid-base in much more detail in Unit 4 in chapters 15 and 16 respectively. But a redox reaction is where there's a transfer of electrons. Redox is formally the shortened name for oxidation reduction reactions. Oxygen is where we get the name for oxidation. I'm not really sure about the origins of reduction, but we call these reactions redox. Reduction is a gain of electrons. Oxidation is a loss of electrons. So metals tend to oxidize. Like we know iron oxidizes, metal rusts. That's oxidation. Nonmetals tend to reduce things, or get reduced. There's a little bit of play in between oxidation and reduction. The thing that's oxidized reduces the other thing. The thing that's reduced oxidizes the other thing. Oxygen is a very good oxidizer. It gets reduced when it oxidizes things. Here are two mnemonics for memorizing, what redox is. Oxidation is a loss, reduction is a gain. I prefer oil rig. Some people like Leo the Liger goes GER. Lose electrons is oxidation, gain electrons, reduction. So sodium and chlorine is a perfect example of a redox reaction. We want a transfer of electrons. So we can use our charges or oxidation states to determine whether things are transferring electrons or not. Elements are always neutral, even in the molecular form. So both of these go from neutral to being ionic. So chlorine in sodium chloride is a -1 charge. Sodium in sodium chloride is a +1 charge. So they both lost and gained an electron and changed their oxidation state or changed their charge. They changed the amount of electrons that is associated with that individual element. And so that's what a redox reaction is. It is we're changing the number of electrons associated with each species. And so if I gain an electron, I'm going to become more negatively charged. If I lose an electron or if I give up an electron, I'm going to become more positively charged, just like we see with sodium chloride. So oxygen is a great oxidant. Metals tend to be really good reductants, but there's always exceptions to this. In general, or always, not in general, but always redox is just a transfer of electrons. It can be multiple electrons. Oxygen typically does a 2-electron oxidation. Fluorine or halogens tend to do a 1-electron oxidation, and that's because oxygen wants to gain 2 electrons to get to its nearest noble gas configuration. The halogens want to gain 1 electron to get to their nearest noble gas configurations. Likewise with the alkali and alkaline earth metals. The alkali metals are 1 away from their nearest noble gas, so they'll do a 1-electron reduction because they want to give up electrons. They get oxidized, but they do the reducing. They are the reducing agent. So combustion reactions are just a subcategory of the redox reaction. We do combustion so much, whether it's gasoline combustion, biofuels, any type of combustion reaction is a transfer of electrons because we're taking oxygen, which is neutral, and we're reacting it with some fuel source. Oxygen is always turning into water and CO2 at the end of the day. And in both of those cases, oxygen is -2 charged. Its oxidation state or its charge, depending on how you want to look at it, is -2. And so there's a transfer of electrons that have occurred there. Oxygen has gained electrons. It's been reduced. Whatever oxygen has gained those electrons has been oxidized. And so typically carbon is what gets oxidized in a reduction reaction or a redox reaction. So here would be an example of a combustion reaction using methanol. So again, we want to balance our equations. Combustion and redox reactions are some of the more complicated reactions to balance. Acid-base reactions, depending on what they are, if they're not just simple one-to-one binary acids and binary bases, they can get pretty complicated. So a combustion reaction is actually going to be one of our challenge questions. I'll present this later in lab and in chapter 8 problem solving. We're going to do the combustion of octane in oxygen. And so I'll give you that the hydrocarbon plus oxygen reacts. You'll have to fill in that carbon dioxide and water are the products, and then you'll have to balance the stoichiometry of the reaction. This one will be a little bit simpler than combustion of octane, but starting with methanol, we want to balance our hydrogens first. That's the least electronegative atom. We want to balance our oxygens last because that's an element. Carbon will be in between. So we put a 2 on the carbon to kind of balance out our hydrogen. So we started out with 2 hydrogens over here, and 6 hydrogens over here. So we're going to go back and forth balancing these. It's a very good idea to have the kind of mass balance table that we presented previously to keep track of it. Because in this case, you're going to balance this side, and that's going to unbalance this side. We'll balance this side, and then have to organize everything afterwards. So we have a few different types of chemical reactions, precipitations, acid-base, gas evolutions, and then our redox reactions, which can then be subclassified into combustion reactions. But we have different types of ways to describe our reactions. So we have synthesis or combination reactions where two things come together to form one product. Decomposition is the reverse of that, where one thing decomposes into two or more things. Displacement reactions are the ones that we're a little bit more familiar with because we've done these. We did a double displacement where we have we have two binary compounds, and the anions or the cations, depending on how you want to look at it, switch place. A and C switch partners, so we get AD and CB, just switching groups. A single displacement is where you have an element and some binary compound or some cationic and anionic species. They switch partners and displace a new element from the original element. So originally we had element A displaces B becomes a pure element. It's a little bit more rare, but we will see a couple examples of these. So, combination reactions, sodium and chlorine combine to make sodium chloride. This is very common with elements. They'll combine to make different molecules. Hydrogen and oxygen will do a combination reaction to make water. The stoichiometry is important, but we can have a decomposition reaction, whereas essentially the microscopic reverse of the combination reaction. I use the example of reacting or combusting oxygen and hydrogen to make water. Well, we can do an electrolytic reaction where we can apply energy to the bonds through electricity. It severs that bond and reforms the oxygen and hydrogen. So we form two things from one parent compound. That's our decomposition, breaking something into more than what we started with. Our displacement reactions is where one thing switches place. So single displacements are characteristic of a single element getting displaced and forming a new element. So zinc has a lower potential than copper, and so when they come into contact with each other, they'll literally just switch places because it's more favorable for the copper to be elemental and the zinc to be ionized than the copper to be ionized and the zinc to be elemental. Copper is very stable in its elemental state compared to most other metals. We have our precipitation reaction, which is almost always, a double displacement reaction. So double displacement reactions are probably the most common type of reaction that we're going to do in this class. And that's because they typically lead to these precipitation reactions. So we have 4 ways to represent those 5 classifications. So we are reaction classes. These are classifications of those reaction classes. So we can compose of synthesis, decomposition, single displacement, double displacement. Any one of those could be combined with an acid base, a redox, a precipitation reaction. One description is not always the right one, so it depends on what you're doing, which description you want to use. So we've talked about chemical reactions in depth. This is going to be the most important thing that we do, is balancing chemical reactions. Evidence of chemical reactions is important, but we're going to have a couple of labs looking into this in particular, so we're not going to cover it much in terms of the examination portion of the class. Chemical reaction or evidence of chemical reactions is going to be covered more in the lab portion of the class. Our equations and balancing is, again, very important. We have aqueous solutions. We discuss solubility. We'll have some labs on solubility, but I don't care if you memorize solubility rules. We'll have tables to describe them. We discussed a few classifications of reactions. These are kind of our fundamental reaction classes. There are a whole bunch of other reaction classes that you can get into, but they're more specific and more niche and can be generalized into these general categories. Again, the combustion reaction is a more specific redox reaction. And then we have, kind of descriptions of how the reactions work. Synthesis is things coming together. Decomposition is things breaking apart. The displacements are things switching places. Again, the most important thing is balancing our chemical formulas. We didn't do any grams to moles or moles to grams, but I really want you guys to keep this in the forefront of your mind, because this is what chapter 8 is going to bring to the table, and this is what we're going to do in every single chapter here on out. You will always have to do some type of mole conversion from starting materials to products. In order to do that, you have to have balanced chemical formulas. And once you have balanced chemical formulas, then you can balance your chemical reactions. So we talked about solubility, reaction types. Those are important, but less so than actually balancing our chemical reactions. If you have any questions on this stuff, please make sure to reach out, and I'll see you in lab this week.